In this series of videos, I'm going to talk about how to use numpy, especially numpy arrays, to solve a series of mathematical and other scientific problems. In this first lecture, we are going to talk about numerical differentiation. So just to point out, in these videos we are not going to use the full power of numpy. We are just going to use simple ideas, and most of the time you will need only one-dimensional or at most two-dimensional arrays. So before we go to solving or calculating numerical derivatives, let me point out that I have already started Python on the interpreter. I've imported numpy as np. I've imported matplotlib.pyplot as plt. These are the standard mantras that we had talked about in earlier videos or in the class before. Basically, from now on, every time I want to talk about stuff which is in numpy, I will say np dot, and when I want to use something from the matplotlib.pyplot submodule, I will say plt dot. So let's first look at a bit of background in numerical derivatives. Well, the formula that you see on the screen right now is actually that for a derivative, right? F prime x is nothing but the limit as h goes to 0 of f of x plus h minus f of x divided by h. Now let me point out that while this is perfectly correct as far as mathematics is concerned, on a computer, especially on a computer doing standard numerics and not computer algebra, we simply cannot take the limit as h goes to 0. So what we are forced to do is take a sufficiently small value of h. So if we do that, what we can do is get an approximation. F prime x becomes this approximation as long as h is not too big. So if h is rather small, f of x plus h minus f of x divided by h will give an approximation to f, this derivative, at x. Now this is called the forward difference formula. Forward difference because you are moving x forward to x plus h, finding out the value of the function there and subtracting the original value of the function to get the numerator. Similarly, you can get a backward difference formula, which is simply f of x minus f of x minus h. So you are moving back and you are finding out how much the function has increased or decreased because of that, and then divide by h, and you take the limit. Well, you don't take the limit, sorry, you can't, so you take a very small value of h. Well, there's another formula, the so-called central difference formula. F prime x is approximately f of x plus h minus f of x minus h. So you go forward by h, you go back by h, and then you divide by 2h, the difference between the two x values that you have used. Notice that if you were allowed to take the limit h going to 0, then provided of course that the limit exists, each one of the three formulas here, the forward difference, the backward difference and the central difference, would have given you exactly the same result, namely the derivative of f at x. But as you will see, because we are not allowed to take the limit as h goes to 0, but have to stay content with a finite albeit small value of h, we will see that there is a big difference in the formulas here. So let's first try to see how to implement this f of x plus h minus f of x by h, the forward difference formula, using Python. So let's go back to my Python interpreter, where, as you have seen, numpy is already imported. So let's say I want to differentiate a function which we are, let's say, sine square x, okay, and I'm using the lambda keyword to define a function which essentially says f is the name of an anonymous function which maps x to the square of np dot sine of x. And there you have it. Of course, you could have used def f of x to define the same function using a return np dot sine x whole square. So now that you have it, first you need an array of x values. So let's say I want to find the derivative at each point or almost every point between, say, 0 to pi, and let's just say I am taking a sufficiently small interval, which means I need a rather large number of points, 1,000 points. And you may recall that the linspace function in numpy essentially does that. So this is saying take points from 0 to pi, which is the pi from the numpy module, so np dot pi, 1000 points, and we are using the option retstep equals true, which, if you recall, returns a tuple. So with the retstep equal to true option, linspace returns a tuple. The first element of the tuple is the array of values between equally spaced values between 0 to n pi and 1000 points in this case, both 0 and pi inclusive. And the second element of the tuple will be the step size. So what we have done is we have used Python's unpacking to unpack this tuple into the two variables xs and h. So after I do this, xs will have the array, h will have the step size. Fine. So now I have a 1000 element array, but this is the array of the x values. Of course, I need the f of xs to do the calculation, or rather, what I call the y values. So y's, a new array. And that's pretty easy to calculate. The value of y at every point in xs is simply found by applying the function, which is a universal function, a standard numpy universal function, which acts on an array as a whole, element wise. So if I say y is equal to fxs, every element of y's is the sine square of the corresponding element of x's. So I now have a series of x values, I have a bunch of y values. Fine. So how do we calculate the forward difference formula derivative, or forward difference approximation for the derivative? Before we do that, let me show you the basic idea involved using another array, a simpler, smaller one, not a 1000 element array like y's, but maybe a small array. Let's say 1, 4, 2, -5. This is just an array which I've picked up, an array of 4 integers, 1, 4, 2, -5. And suppose this is the value of the value which a function takes at 4 successive x values. So how do you calculate f of x plus h minus f of x? Which means I need to subtract 1 from the 4, 4 from the 2, 2 from the -5 to get the 3 differences that we are looking at. Notice that although we have a 4 element array, we only get 3 differences for the simple reason that you cannot get a difference for the last value. There is nothing after the last value. So there is no f of x plus h. Now, just to point, you can of course write a loop and run a loop, for loop over the entire array. And if you do it right, you are definitely going to get the corresponding differences. But using NumPy's array slicing and the standard way of doing mathematics with arrays, you should be able to do it with a lot less effort. So just to point out, if I slice the array this way, which means you start at element number 1, which remember the second element, and go to the end, you get the array 4 to -5. On the other hand, if I did this started at the beginning, so nothing before the colon, and ended by dropping the last term, so colon minus 1. Minus 1, remember, is the last term, and the stop index which you have in a slice is the index before which the slice stops. I get 1, 4, 2. But remember, what we had to do was subtract 1 from 4, 4 from 2, 2 from minus 5, which I can get easily if I subtract. If I take Z1 colon, the last 3 elements, and subtract from that Z colon minus 1, the last 3 elements. So the first one was, this thing was the first 3 elements, this one is the, sorry, this one was the last 3 elements, 4, 2, minus 5. This one is an array which contains the first 3 elements, 1, 4, 2. And if I subtract them, I do get exactly the differences that I want. So now that we have a nice and easy way of doing this subtraction, let us try it out on our array Y, which has 1000 elements, but the idea stays the same. So let's say we want to define a new array containing the forward difference approximation to the derivatives dy's, and what do we do here? We take ys1 colon, subtract from it ys colon minus 1, and of course I have to divide this whole difference by h, which I have already saved by using the step equal to true argument. Notice ys1 colon has exactly 999 elements, so as ys colon minus 1, so this subtraction is perfectly legitimate. And now I have dy's. So how do we check whether this is correct? Let's just plot, or how correct is this? Let's just first try to plot the value of the function and the derivative together. So since we already have the pyplot submodule imported as plt, I'm going to just use the standard commands plt.plot. So this is the original function, the x's array being plotted along the horizontal axis and the y's array being plotted along the vertical axis. So I've got a matplotlib object for this. Well, I need to plot another graph which is dy's, the derivatives, along the y-axis, and the x. Along the x-axis we want to show these two together so that you can see how good a derivative this is. And I try this and I immediately get a rather large string of messages, but essentially it tells me that there's an error. It says x and y. Here x and y does not mean x's and y's, it just means the first argument and the second argument, which happens to be x's and y's. X and y must have the same first dimension, but have shapes 1000, 999, So realize what has happened. Your x's array did have 1000 elements. The shape of one dimensional array, well, shape of every array is a tuple. So just because it has only one number, it's a tuple with one element, 1000, But the dy's array does not have 1000 elements. It has 999 elements, and of course matplotlib is complaining because the two arrays have different lengths, and it is easy to see why there's this problem. After all, to calculate the forward difference formula, you needed f of x plus h minus f of x, which means that you did get the difference for every one of the corresponding x's element except for the last one. So what you really need to do is not plot x's with dy's, you have to plot all the element of x's except for the last one and dy's. So now we have two plot objects, two line objects actually, two plots. One is x's versus y's, the other is almost the all of x's you have x's, almost all of x's except for the last element, and dy's, which are really the derivatives calculated according to the forward difference approximation. So let's plot the two together. So we have already plotted them. Let's just use the plt.show to see the two graphs together, and this is what they look like. So this is your sine squared x function, the original function in blue. Along with it we have the forward difference derivative calculated and shown here. Okay, fine. So but is this any good? Or it looks like a rather nice derivative. If you let me just show you this again. Oops, the same mistake as before. So we plot x's and y's. We plot all of x's except the last element and dy's. We show them together. Notice that sine square x is 0 here and here. Not only is it 0, it's flat here and here, and the value of the derivative is also 0 there. It reaches a peak at this point of inflection where the function rises the most, then it drops off. At this point is again back to 0 at the peak, and so on. It sort of looks okay. Well, we also in this case happen to know exactly what the derivative is. It happens to be the function twice sine x cos x, or sine twice x. So we can define that as well. So this x maps to np dot sine 2 star x. So this is the derivative function, and so what we can do here is plot the derivative approximation and the derivative function. So let's take all of x's again and take df, the function acting on the array x's, which gives us of course a new array with every element being sine twice the corresponding element in x's. So we now plot these two together and see whether, at least by naked eye, we can make out any difference. So let's show them, and if you can see, even after I blow this up, there doesn't even seem to be two curves here. There seems to be only one, and that's because the two curves have sort of merged almost completely. This, of course, remember, is because with the range value we have used is pretty tiny. This all looks very nice, but how big really is the error? And that's also pretty easy to find out here. Let's just plot not just dy's, but from dy's let's subtract the exact value, which is df, and df of course now cannot be calculated over the entire array x's. So we calculated only over the first 999 elements, leaving the last element out. So now you have two arrays, dy's, which has the approximate derivative, df, which is the exact derivative, and now I'm plotting this quantity. Well, it doesn't look very small as a difference right now, but notice the difference goes all the way from 0.003 up here to somewhere around minus 0.003 down there. So since the typical value of sine square x function is of the order 1, the error here is roughly 1 in 1000, or of that size. So fine. Can we do any better? For example, will the backward difference formula be any better? Now for the backward difference we need to calculate f of x minus f of x minus h, which means if we go back to our original array, the small array z, I have to again calculate 4 minus 1, 2 minus 4, minus 5, minus 2. Which means that the array that I have to calculate is exactly the same as before. Z1 colon, which is 4, 2, minus 5, minus Z colon minus 1. Capital Z, of course. This is case sensitive. The question is there any difference in this case? Because we are doing the same differentiation, same difference. So how is the backward difference formula any different? Well, the only difference you have to realize is that in the previous case, 4 minus 1 would have been assigned, after division by the h of course, would have been assigned to be the derivative at the 0th position, at the very beginning position. Here 4 minus 1 is actually the derivative at the 1th position. The value is 4, you subtract the value one step behind 1, so 4 minus 1 by h is the value of the derivative here at the 1th position, not at the 0th position. So in this case I don't really have to calculate a new value of dy's. All I need to do to realize that the corresponding x values do not start at the beginning and go on till one shot of the very end. Here the x values start at position 1, go on till the very end. And of course if I am calculating the so here we are plotting dy's against the last 999 values of x's. This is how you get the backward difference derivative. We are also plotting df again for the same last 999 values of x's. That is starting from 1 and going till the very end, and we are showing them again. Frankly, we do expect one single line, and unless you are looking very, very carefully, or unless you have a wonderful memory, you will not really be able to see any difference between this line and the forward difference curve that we had drawn a while ago. So what about the error? Is it really very different? So let's see that. So this, what I want to plot here is dy's minus df at this, and let's show this. Well, the error sign has changed, the size is of, and the sign changing is also not really something which should surprise you, but anyway what you can see is the size of the error is the same in both the cases, of the order of 0.001, the 1 in 1000. So the forward difference and the backward difference formula, although they give slightly different results, they are qualitatively much the same. They have slightly different errors, but their errors are also of the same order. So what about the central difference formula? Let me remind you, in the central difference formula you take a value to the right of x, that is at x plus h, you take a value to the left of x at x minus h, and subtract these two values and divide by twice h. So just to remind you of what we want to do here, let's take a look back at our toy array, the array with only 4 elements. In this case, the derivative corresponding to this position, the position number 1, the 1th position, will be the value of z at position number 2 minus the value at z at position number 1. So you have to subtract 1 from 2. Similarly, to get the derivative here, you need to subtract 4 from minus 5. So basically what you can do is this: you do z2 colon, there is slice which is 2 and minus 5, that is starting at element number 2, which is this one, 0, 1, 2, and then going on till the end. On the other hand, if I did colon minus 2, I start at the beginning, drop the last two entries, and I get 1, 4. And if I subtract these two, I get exactly the differences that I want. 2 minus 1 and minus 5 minus 4. So what I need to do is this. Z2 colon minus Z minus. And I really get the difference I want. 2 minus 1 of course is 1, and minus 5 minus 4 is 9. Now this was with our toy array. We really need to do it with the actual array of function values, which remember is y's. So let's now define a new array, dy's as before, but now let's add a c to remind ourselves that this is a central difference formula, and this will be y's 2 colon, drop the 0th element, drop the 1th element, take the last 998 colon minus 2. Of course that's not all, that's just the numerator. The denominator will be divided by 2 times h, and that's our dysc. But what are the corresponding x values? Notice that the very first x value in xs cannot have a central difference derivative because it does not have anything to the left. Similarly, the very last one cannot have a central derivative because it doesn't have anything on the right. To calculate the central derivative, you need both the right hand and the left hand value for y. So the 0th one and the very last one are out. So the corresponding x values are really the values starting at position 1, that is drop the 0th, and the position last but 1, so drop the minus 1th. So if I want to plot this, I cannot plot xs versus dysc, I can only plot this. And this is fine because this has exactly 998 elements, which is exactly the same as the number of elements in dysc. So this is the plot for the central, or I have set up the plot for the central difference. I can at the same time plot x's with y's, and if I show the two together, I get a very similar curve. Of course the colors have been swapped because here I have plotted the derivative first, so that comes in blue, and I have plotted the value of the function after that, so that comes in orange. Now again you can see hardly any difference between this picture and the picture that we had for forward and backward difference. And as you have already guessed, certainly if I were to plot the exact value of the derivative against the central and the central derivative approximation, both of them will give you almost the same curve. But to see the error, what I really should do is this: from this subtract the difference of the exact derivative function, which remember is df, and I need to evaluate this, of course not at all values of x's, but or all values barring the 0th and the last one. If we now show this, we get a graph like this. Now the shape of this graph is different, but that's really not the important thing. Look at the scale here. If you look at the scale here, you get 0.000006. So the scale is 1 in a million. So realize that despite the fact that if you just looked at the curves with your bare eyes, you will not be able to tell much of a difference between the backward difference, the forward difference, and the central difference curves. In reality, there's a huge difference. The backward and forward difference curves are almost equally accurate. However, the central difference formula is actually way more accurate. And the reason for this is what we are going to discuss in the next auxiliary video.